Okay, so I am going to start here with this lab, is it five? Yes, using spectrophotometry to determine the equilibrium constant. So hopefully you're starting this lab after you've done your lecture part, okay? This lab is a challenging one. I tried to go through it and then there was some little glitches along the way, so I had to kind of reset. Anyway, I'm hoping this will work. Request provisional data. Okay, I hope this will work. Okay, we are working on this virtually, and I figured out some of the issues we're having is due to the fact that we're trying to do an online lab with face-to-face instructions in some cases. So having to go back and forth is a little challenging. But anyway, we're given the information here. So this reaction, the main reaction we're having in this experiment is between iron 3 plus and thiocyanate. Now, this is, of course, aqueous solution, and the thiocyanate SCN minus is aqueous solution. And when these react, they form a complex. Now, in the background information, both iron and thiocyanate are said to be colorless. Now, when we work on this on campus, the iron has a light yellow color, but we will go with what they say is virtually colorless. Like most people see it as colorless. Okay. And then the iron thiocyanate complex, that's the one that has a reddish orange hue or color to it. Because it has a color to it, we can use the colorimeter or spectrophotometer to figure out the concentration from the color. But I'm getting ahead of myself. We're given the concentrations, the theoretical concentrations for the iron nitrate and then the sodium thiocyanate. So the nitrate part is the counter ion, the sodium is the counter ion, it's more like the escort ion. These are the ions that we care about, right? And so what I've drawn here or what I've written here is a net ionic equation. Okay, so from here we're given the actual concentrations for iron will be 0.198 molar. And then for the thiocyanate is, oh, they're using a different number, 6.98 times 10 power negative 4. Okay, I have to adjust. That's okay, I'll adjust. Okay, and then we're told that we're going to prepare solutions, 5 solutions with the first, I guess 6 total, the first one being blank. The first one only has iron nitrate. The second, all the way to the fifth, has, well, they call it 1 to 5, has increasing amounts of sodium thiocyanate. And the total volume of solution is accomplished by adding nitric acid, 0.1 molar, until we get a total of 25 milliliters. Why is that important? Because in the lab, when you mix 2 liquids together, in this case, 2 aqueous solutions, because you're mixing one chemical that's in the liquid state with another chemical in the liquid state, they tend to dilute each other. So the concentrations written here before they're added to each other is not the concentration once they're added to each other. Once these chemicals are added to each other, they dilute each other. So the new concentration for iron nitrate will be different. You have to use M1V1 to figure this out. Okay, so I try to be proactive and figure out the new concentration in water. And just so you know, I use M1V1. So I'm going to show you how the first one is done. This is the actual concentration, right? But I use in the M1V1, I use the original amount, which was what, 0.2. So M1V1 equal M2V2. We're trying to figure out the new diluted solution concentration of, so we're trying to find the diluted concentration of iron in the solution once you mix the 2 aqueous solutions together. Remember, they dilute each other and their combination essentially causes a dilution of both ions. And we need to move on with the diluted version of the ions. So for iron 3 plus iron, I know so many words. We're trying to figure out its new diluted volume. Sorry, we have the volume. We're trying to figure out the concentration. So that's going to be M2, and M2 is M1 V1 over V2. So using, well, I guess you can use this one here. In my little table, I'm going to show you guys, I use the original concentration that was what, 0.200 molar. And then in the table here, it shows in all the trials, the volume of iron 3 will be 10 milliliters. I'm trying to keep this short and to the point, right? I'm gonna use Excel table because when I was doing my first try, I was using a calculator. It became too much, and the video was getting longer. So the Excel spreadsheet is a way to kind of shortcut the process of doing repetitive math. And I'll show that to you. Anyway, we have the first molarity, we have the first volume, and the total volume is 25 milliliters. So when you use this, since the amount of the iron nitrate used in each trial is constant, the concentration is constant, the volume is constant, our diluted volume or concentration based on the total volume should be 0.08. Okay. So go ahead and work it out. Let me show you the table I have here. So instead of having to work this out over and over and over again, I just set it up over here. And then for this is my wanted. For my wanted molarity, the diluted version, I just put in here C4, which is what? C4, yeah. M1, V1. So it says C4, this here, D4, this. So multiply those two, and then divide by 25. So that would be F4. So if you click on this one, you see here, yeah, in parentheses, C4 times D4, close parentheses, divide by F4. So instead of having to do this over and over again, I just plug them in here, drag this down. Oh, no, drag this down. I got my answer. For the second one, I did the same thing. Now for this one here, they gave me a different number, y'all. Y'all saw the different number, right? So let me go ahead and copy that. And then they said 6.98 times 10 power negative 4. So now I have to adjust that. So this is going to be 6.98, 6.98. So this is going to be 6. Okay. So that changes my amount. Same thing. I have the total volume, the amount added per run, and I'm able to figure out my new amounts here, right? Without having to do too much math, right? So let's go ahead and verify that. Yes, in the first run, I have so many documents here. I'm trying to make this as short as I can. Let me minimize this page a little bit. I feel like I need a wider computer. I have 2 screens here, but right now this is not very helpful. Okay. So for this one here, you can see for sodium thiocyanate, the first run is a blank. We have 0 sodium thiocyanate. Second run is, what is it called? 1 mil, then 2 mils, then 3 mils, 4 mils, 5 mils. So this is the new concentrations right here, okay? So once I have that, then I'm going to copy this over to the next page. Okay, I need to make some modifications here, y'all. Give me a moment because this new numbers has now changed my numbers to 2.792 times 10 power negative 5, 5.58, 4 times 10 power negative 5, 8.376 times 10 power negative 5. I'm just copying these over so I don't have to come back here a lot. Then we have 1, 2, 3, 4. We have 1.117 times 10 power negative 4. Last one is going to be 1, 2, 3, 4, 1.396 times 10 power negative 4. 1, 2, 3, 4. Okay, so I'm going to copy this over here, okay? It will change all my numbers. Now try to go ahead of time and figure out the calibration curve, but as you can see, I have to make some modifications. For this first one here, I'm kind of jumping ahead, but give me just a moment and I'll explain what I'm doing in a moment. Okay, I'll give you guys the short version of it. Okay, so this is 2.792, and that's going to be exponent negative 5, right, for the first one. Oh, no. This is all, okay, so 2792. Okay, I forget. This is the standard format. Okay, and over here, let me type it over here. That might be better. 5584. 5584. Okay. I feel like I should add some decimals here. Should I add some decimals here? Okay. And this next one here is 837. Is it 6 or 0? I'll put 6 for now. 8376. Okay. 76. Then here we got 1117. Okay. So 1117. And then for this last one, we got it's 3 zeros after the decimal, 1396. Okay. Okay, so I feel like once again, let me make this bigger for a moment. I need to add decimal places. Okay, for these right here, let me add decimal places. Nope, I did the opposite of what I want. No, why is it going out that way? Okay, I guess this works. Okay, so here's it is. So I'm trying to go in order, right? They gave me the concentrations right here. I did it. They gave me the actual concentrations. I used those to figure out the new diluted volume. Okay, so so moving on from here. Okay, so once we have a diluted volume, we go through here. They give us the amounts of each chemical used to get the total volume of 25 milliliters. Iron nitrate, as you can see, that amount is kept constant. And when you read through here, the iron nitrate amount, if you look at it, is actually a lot. It has a higher concentration relatively, right? And a greater volume. So for each run, we have more iron 3 nitrate than, iron 3 nitrate than we need. And we have less of sodium thiocyanate, meaning that sodium thiocyanate will be the limiting reagent before we get to equilibrium, right? We don't have enough compared to the iron 3 nitrate. Okay, so we have excess amount of iron 3 and then not enough of thiocyanate, but then the reaction continues. Okay, so we're going to go ahead. You use the spectrophotometer to measure the amount of product. I mentioned earlier that only the product has the color, right? Only the iron thiocyanate complex has the color. So let me scroll this down. Yes, back here. Only this has the color. So the machine is only really able to record. It is calibrated and set up to record the product, the complex, this one here. Okay. So at 447 nanometers, we're able to record the product made. And then we'll kind of work backwards. So here we're seeing a results for the product at 447. The blank gives you no absorbance. And then the idea is the product that's made that has a color will absorb the ultraviolet light passing through at 447 nanometers. So the more chemical you have present, the higher the absorbance. So the absorbance and concentration are directly related. Okay. And when you go back to Beer's law, I want to give you the short version of Beer's law without going in details. A, which is the absorbance, the numbers we're seeing here, is directly related or linked to, well, I'm not writing this in order. Let me go back into the concentration. Both E and B, this is the molar absorptivity constant. That's the E symbol. And then you have B. B is the path length. So when you look at the experiment, the chemicals are placed in something that looks like a square test tube. It's actually called a cuvette. So we're trying to figure out how long that light is in the solution. So not more like the distance traveled, right, in the solution. So that is the path length, the thickness of the cuvette. And that will be the symbol B. Since the cuvette is standard, B can be figured out by just knowing what the cuvette is. Long story short, from this relationship, Beer's law, we see that absorbance is proportional to concentration. So if the absorbance goes up, we expect the concentration to be higher. If there is a relationship between these two, then if we know the absorbance, we can mathematically figure out the concentration. Let me give you guys a bottom line. Why are we trying to use this machine to find the absorbance? We don't really care about the absorbance. It's just a means to an end. What we really want is the concentration. Do we have a concentrationometer in the lab? I just made that word up. No, we don't. We don't have a device that directly measures the concentration. But what we do have is a device, the spectrophotometer, right? Written as spectro. So spectrophotometer. This uses ultraviolet light. So we're using the ultraviolet spectrophotometer, using the ultraviolet spectrum, that light, right, photon, to measure, or photometer, right? Meter is like scale or measuring. So we're using light from the ultraviolet spectrum to measure, in this case, the absorbance. Once the absorbance is measured, it's a number that can then give us the concentration. And if we had a way to measure the concentration directly, we will use that way. This is just the more standard way, the more traditional way for figuring out the concentration. Okay, so we're learning that process. Okay, so hopefully you're getting why we're here. Okay, so we go through here, but even though we know that there's a direct relationship between the concentration and the absorbance, we want to know what these factors are in this lab. So what we're going to do in this lab, or what they're going to lead us to, is something called the calibration curve. The calibration curve gives us the actual relationship for our experiment between our absorbances and concentration. So the first half of the experiment is to get that innate relationship between these two. And they call that the calibration curve. Okay. So once we have our absorbances, let me check our absorbances versus what we have here. Okay, so I have my old numbers. Did I write the new numbers yet? Are these the new numbers? Oh, yeah. Okay, thank God. So we're going to do a graph. This is a calibration curve to give us the relationship between the concentration and the absorbance. So make sure your concentration is drawn first in Excel. And I went ahead to type this in because I'm a slow typer. I don't want you guys to sit there watching me type one letter at a time. I know. So I went ahead. I've already written the new amounts for this, right? I'm trying to double check to make sure this is correct, right? 558,279. Okay. I feel like I need one decimal place to make sure I have all the numbers, right? Let me add one more. Yeah. Okay. 2792, 5584, 8376, 1117, 1396. Okay. I feel a lot better now. Now, since I did this is standard solution, right? They gave me new absorbances. So this one has to change to 2. I need to change this to 2, right? And this is still the same. This is the same. This is the same. And this is slightly different. So I'm going to change that to 6. So just like I have it set up here, you're going to draw your calibration curve. To draw the calibration curve, you see what I have right here. Ooh, this looks small. Let me show you how you would do it, okay? Let me see if I can delete this out here and start over. For your calibration curve, you go ahead and highlight the numbers only, and then you will insert. So I'm going to insert a scatter plot. You can see this one right here, scatter plot. Select the first one, and then you're going to move all the way. Can I make this bigger? Okay, so our chart title can be ABS for absorbance versus concentration. Okay. Now remember I mentioned before, we're trying to figure out the absorbance of the product. So our product will be of FeSCN. Okay. 2 plus. That's our product right there. Ooh, 2 plus. Shift. I told you all about my typing. Okay, I'm going to add labels to the Y and X axes. Data table. I think I have the title, right? Oh, yeah. This is a vertical. Vertical should be absorbance. Absorbance. Yeah. I'm trying to be efficient in what I'm doing so that you guys can. The numbers are kind of overlapping here because of. I wonder if I can convert these to scientific notation. I don't know how to do that. I should, right? If you can find a way to do that, it will help you. It will help this be easier for you because I know what I'm looking at. It's just the numbers are kind of overlapping. I don't like the format. Can I make this? Oh, can I make this vertical? Like that? Oh, but then it shrinks that. Okay, well let's not do that. Let's not do that. Let's just do it regular horizontal. Okay. Yeah. Okay. Let me see if I can do it this way. This is point, and this is going to be E negative 5. Can I do it that way? Oh, these are 2 decimal. It's the same thing. Okay, well, should be a way to write these numbers in scientific notation. This is not really helping me. Okay. Can I change the format here? Number. Scientific. Oh, I got it. Okay, sorry. Sorry, focus, teacher, focus. Okay, listen, guys. Sometimes I'm proud of myself. I am not gonna lie. I am proud of myself. And what? Yes. Okay. Anyway, let me focus here. Yeah. So we have these numbers here. And yeah. So hopefully they're not overlapping that much. Okay. But y'all saw my numbers, right? Now I have to add to this. I have to where am I at? Does this allow me to insert? I think I kind of got a little bit lost here. Okay. I have forgotten how to get to the part that allows me to. So we have the title here. We have a format. Okay, so I'm trying to figure out how to title this. Okay. Anyway, let me go. Oh, yeah. Add chart element. There it is. Right. Horizontal. Ooh, that was close. And this should be concentration right here, right? So CONC, concentration. Okay. So we got this. Now I'm going to right click on this and then add trend line. And then for this one here, I want my R squared displayed and I want the equation of the line. So we're going to move this over here. Can we make this bigger? Okay. So I'm going to copy over my equation, right? So my equation is now all different. Oh. Okay, so the equation is y equals 3871x minus 0.0297. And my r squared is equal to 0.9903. Okay? So I'm going to come back to this page for right now. Let's put a pin on this and then we'll come back to it. So now that we have this relationship over here, we're then being asked to determine the equilibrium constant. Okay, we're given the concentrations of iron nitrate and then sodium thiocyanate. For both of them, we have 2.00 times 10 power negative 3. These are the actual amounts, but then we're told that these are the molar concentrations used in part B. So you want to use that part for the dilution. Use 1.98 times 10 power negative 3 as the iron concentration. And then for the dilution, use 6.98 times 10 power negative 4 as the thiocyanate. Okay. So let's see. And then we're given the solution concentration. So we have these numbers here. Let me see. Did I go ahead and do the math here? Did I? I don't think so. Let me see if I can go ahead and use the same table I used earlier, right? Why not? Okay. So since we have these numbers right here, let's go ahead. Okay. Yeah, we have the molar concentration. So we're told to prepare the test solutions using the table, using 10 milliliter. That's for on campus. We're not using those. Okay. And so according to the amounts we have here, we have these test solution concentrations. So we have, not concentration, absorbance measurements for test solutions. Okay. So remember, in both cases, we're measuring only the product, 0.061. 0.061, let me see if I can write that somewhere. We have 0.061, 0.165, 0.282, 0.407, 0.525. Okay. And this is for run 6. I'll just call it 1, 2, 3, 4, 5. They call it 6, 7, 8. Okay. So this is the process of us creating the calibration curve. They gave us the concentration of the stock solution. So this is kind of reviewing what they gave us, right? And from here, I already have my concentration, so I can just copy these over, correct? I can just copy this over because I already have these. Paste. And this is for the product, right? So yay. Copy that over. Paste. Copy this over. Paste. Right? This is the diluted concentration of thiocyanate, which is the same as the concentration of the product. Because remember, thiocyanate is the limiting reagent, so it controls how much product you get. I'm trying to make sure I'm copying this. Oh, I'm sorry. I'm looking at both screens, but y'all can't see, right? So I'm just writing the diluted concentrations that we have here. And remember, I got this by doing M1V1, and the concentrations I use were, I think, for this part. Oh, let me make sure I'm clear about that. For this part, when I'm doing M1 for the thiocyanate, I think this is a typo because they tell us KSCN, but we're dealing with NaCN, sodium thiocyanate, not potassium thiocyanate. So we're just going to use the thiocyanate part. And the initial concentration is 6.98 times 10 power negative 4, right? That's what I have up here. So when you're doing your M1, V1 to figure out the M2, M2 equal M1, V1 divided by V2. So our initial concentration here is going to be 6.98 times 10 power negative 4. Our initial volume past the blank, I think from the table that was 1, right? So times 1 divided by 25 is the total volume. So when you multiply that out, we get 6.98 exponent negative 4 times 1 divided by 25. And what do we get? We get 2.792 times 10 power negative 5. Okay? And that's what I have for this second one here. Okay? And I did the same thing, of course, replacing this with 2 milliliters, 3, 4, 5, and we go all the way through here. That's how we get these numbers, by using the dilution formula. And they wanted us to use the initial concentration of thiocyanate. They gave us this number, not the number that was written up there. Okay? Okay. So remember, I've already drawn my graph because I kind of went through already and did some of the work. So I've already drawn my graph and I have this new relationship, right? So let me minimize this a little bit. I'm not quitting Excel. Don't quit. Don't quit. We need these numbers. So from the graph, what is our slope? Our slope is 3871. So I'm going to write here 3871. Okay. And then the y-intercepts, negative 0. Okay, so we have a negative 0.0297. Based on what I have here, r squared. Our r squared is 0.9903. Okay, not bad. Okay, so now we're moving on. So now we have a relationship between y is absorbance and then x is concentration, right? I'm going to write this down here, that we have A, which is what y is equal to, what did we say the slope was? 3871x minus 0.0297. So what we have here is 3871c minus 0.0297. Give me just a second. I'm going to pause. Oh, I need to pause the video. Not pause it. Let me pause. Okay, so I am back. Let me see, where did I leave off? I left off right here where um we were seeing the relationship between concentration. So this is concentration right here, absorbance right here. So for us to find the concentration, which is our goal, we will take I'm going to just give you the relationship. We'll take absorbance, right? And then we'll move this over. So we'll add to it 0.0297 and then divide this by 3871. And this will give us the concentration. Now remember, the machine is only measuring the amount of the product. And this product amount is the amount essentially made at equilibrium. Okay. So let's see, where would I leave off? We have these numbers put in there. The next thing is finding equilibrium constant. So for that part, you have to have equilibrium amounts of each chemical. Okay, so for this one here, remember, this is our relationship. So I have to kind of set this up in a table because I don't want to have to do this over and over again, right? So let me see if I can figure this out. Because, oh, we have the absorbances, right? Okay, I kind of have to figure this part out. Yeah, I have this here, but on the left, I have to have absorbance. So I'm going to put the absorbance here, right? ABS. And then the absorbance should help us somehow find the concentration, but they should be uh, the constant, maybe? Let me start with this. Okay, so we have the absorbance. From the absorbance, we have the constant. I'm kind of making this up, y'all, so give me just a moment to think through this constant. And then here we have the concentration. And we're trying to figure out the concentration of the ions I assign it, right? Remember, it's the product only. So I'm trying to convert what I showed you guys earlier, this into that. So our absorbance will be the number that we get here. Our constant will be what? Oh, we have two numbers. Oh, so we need to have our slope and okay, you know what, guys? I'm getting it. We don't need constant here. We need the slope and we need the y-intercept. I was still thinking about Beer's law. Forget Beer's law. Slope and then y-intercept. Did I spell it all right? Okay. And then this will be our concentration. Okay. Concentration. I am hosting, so I'm a little bit distracted. My mom is helping me cook and stuff like that. So it's been like, yeah. Okay, so concentration here. Concentration. This is what we'll solve for. So in my calculation, I have to make sure absorbance. So absorbance is this one here, right? So this is equal to absorbance shall be added to, let me get this to the side so we can kind of cheat from here. Absorbance shall be added to 0.029. Okay, and this is what? This is a y-intercept. So y-intercept, right? And together the sum of these two shall be divided by the slope. So divide by the slope, right? Did I get it right? Yes. Okay. So slope value is what? 3871. Is that what we get? We said 3871. And that's true for all 5 experiments. 1, 2, 3, 4, 5. 3871. The y-intercept, oh, well, this is what we're adding to that. So I'll just leave it as, even though technically it is, yeah, I'm going to write the positive number because it's going to be confusing. 0.0297, okay? I know the y-intercept is negative, but remember in this calculation here, this number is positive, right? Unless we want to leave it as negative and then make it minus plus, that's confusing. Remember, I'm trying to take this and add it to that. So this plus that, right? That's this one here, divided by, yeah, this plus that. So the top numbers are, oh my goodness, okay, absorbance, right? Which I don't have yet, plus this number right here divided by this. Okay, so I think I got it. Let's see. Give me just a moment, okay? I need to put in the absorbance. Where is the first absorbance? So we're kind of working backwards to figure out the concentration. Where is the first absorbance? They have to have given us that. Well, this is what we got. This is what we got. So right here, we have these amounts here. So this is the actual experiment that was done. Oh, from here, they gave us the first absorbance as 0.061. Okay. I guess I can go from here and then here, solution 7. So, okay, this is 6, 7. I see. So 6 is 0.061. 7 is 0.165. 165. How did I get this? 65. Okay. And then 8, what's the absorbance? 0.282. 9, 0.407. 10, 0.525. Okay, so this is so much easier, right? It's a little bit less overwhelming because, oh my goodness, when I was doing this earlier, I was like, this is a long video. Okay, so you can see how I just got the concentrations here, right? And these are the amounts that we have at equilibrium. Okay, now this part is a little touchy, so I'm going to go ahead and plug these in here, but I can't do this yet. Let's go back to experiment 6, which is where we left off. So they gave us the molar concentrations of iron nitrate, this one here, and then this one here. It says use the ice tables below to calculate the equilibrium concentration. This should be concentration, the typo. For each solution, you will use your absorbance reading and best fit line from the calibration curve. We use the equation to get these, right? You see that? Okay. To determine the equilibrium concentration of this iron thiocyanate. This is the equilibrium amount. We got it already. This is it, concentration. We just did. Where's the bracket? Guys, doing it this way is so much less overwhelming. But as I said, it took us a long time last time, and I was like, there must be a better way. So I didn't post that video because I didn't want you guys to look at that and then feel so overwhelmed by it. It was still a work in progress. Christmas happened. You all know one thing to another, right? But give me just a moment. I want to finish this part up and then show you how I use Excel spreadsheet to not have to work so hard. Okay, so we got this here. Then calculate the K equilibrium using equilibrium concentrations for each test solution. You have 5 values of K equilibrium. Okay, but the issue here though, guys, is I think they want us to use these concentrations in the beginning, not these they gave us. I don't know. Let's see. So I have a table here already, right? And I already kind of pre-loaded it with these numbers. Let me see. For the first one, I'll try this number here. They changed it from the first one I had. So I have 1.98 e exponent negative 3. I'm trying to use the table for that too. That's this one here. This one here is initial amount 6.98 e negative 5. Somehow though, I feel like they don't want us to use these numbers. I don't know, but we'll see. Let's go with this and this for now, okay? So having this amount here, once again, we're acting like, oh, when this is our iron 3 plus, our thiocyanate, once again, we have more iron 3 plus and thiocyanate. So before the reaction starts, the amount, remember this is an arrow here, the equilibrium arrow, the amount of thiocyanate present is 0, right? And then we have a negative X here, negative X based on the amount of thiocyanate that actually reacts. We don't know the amount. So for right now, we use negative X as a placeholder, negative X here as a placeholder. Oh, they should allow me to put this number here. Okay. But negative X here actually has a value, right? It's a number that we find here. This here will be plus X. It should be plus X. When I put this in there, they'll mess up, right? So for these ones, let me delete these because these are not really that. I try to pre-populate this, okay? So I'm going to put a number here. The number here is based on the math we just did, okay? We work to figure out what this number is. So let me see if I can copy and paste this number. Copy this number. If I can paste it right here, man, it will save me. Paste. Oh, come on. It won't work. So I have to copy this number over. Let me write it on a notebook and then I'll copy it over. So we got 2.343 times 10 power negative 5. 5.0297 times 10 power negative 5. 8.052 times 10 power negative 5. 1.128 times 10 power 1234 negative 4. 1.433 times 10 power negative 4. Okay? Y'all, let me try to move over here and see how this plays out. So I'm going to write the number here, right? It didn't work when I copied it over. The number is supposed to be 2.343 exponent. Where's the exponent? Oh, exponent. This is capital E minus 5. Okay. So when I put this number here, this is technically x. Remember, we are adding x to the product side. So I have to put here plus this number here, right? And then here we're subtracting the same number and subtracting that same number here. So I'm just copying and pasting. And then the equilibrium amount is going to be this. Where's the plus? Plus this, right? And then same here. Equilibrium amount is going to be top number plus this number right here. Okay. So instead of me working so hard to recreate this 4 more times, who has time for all that? I got people to entertain. So let's do this. Let's try to copy this and paste. Can we do this? Copy, paste, and then paste again. We're leaving space so we remember these are different experiments. Paste again. The goal here is to be smart about this. I really hope this works, y'all, because I'm making this up as I go. I'm just trying to find an efficient way. Okay, so we have the first experiment, right? That's this one here. And let me see what I have for this. So here, it shows my numbers are 1.98 exponent negative 3 minus x. And our final should be 1.96 exponent negative 3. This doesn't, we'll see. We'll see what they say. Oh, this is a plus. 6.98 exponent negative 4. And this one's going to be minus x also. And we have 6.75 exponent negative 4. Okay. So what I'm going to do, guys, before I commit to this, I'm going to try to submit the first one just to see how well we're doing so far. 0. This is going to be plus x. And the amount here is 2.34 exponent negative 5. Okay. Oh, and if we do this one here, our K equilibrium then, let me see if I can do that. K equilibrium, trying to get all this done here together based on what we have here. Wait, why wouldn't it allow me to put in type in Q? Press too hard. Is equal to, okay, so bringing this back in, based on our equation that we had back there, when we have these numbers here at equilibrium, let me ignore this part here, erase. Once we have our equilibrium numbers, right, our equilibrium expression helps us to get to the K equilibrium. The expression is equal to, using only equilibrium numbers, K equilibrium is equal to the concentration of iron thiocyanate at equilibrium. So the last row, the third row, the one that goes with E, divided by the iron concentration at equilibrium, and then the thiocyanate at equilibrium. Okay. So I need to have columns that have these numbers, right? Let me see if I can translate that in here. So it's the product first. So from here, I need this number here. What is this number? So this is equal to this number, product, right? Divided by, where's the divide? Divide by, open parentheses, this one here, times this one here. Let's see if that works, y'all. Please work. What in the? Oh, okay. So 178 times 10. Is this really possible? So what we have is the product, right? 2.34 exponent negative 5 divided by 1.96 exponent negative 3 divided by 6.75 exponent negative 4. Wait, my numbers are coming out differently than what they have here. I feel like my number is, okay, so I'm getting 1.78 times 10 power negative 1. So I'm getting 17.8. Okay. Okay, guys, let me go ahead and try this first one and then see how it works out, right? And then, did it go through? I'm gonna, of course, fix the ones that have issues, right? Okay. Let me go through here and see how we're doing. Because I'm trying to make this video quick. As I said, I have, look at that, look at that. Great. And 1v1. Great, great. Oh, they accepted our slope and everything else. Great, great. Just trying to go through here. And please, oh no, they didn't like the initial concentration, but they like the change and they like this one here. Okay. So they don't like either initial concentration. Okay. It's kind of weird, right? Okay. So they don't want me to use these numbers. That's why I was kind of trying to figure out which one do I use. They don't want me to use these ones for initial concentration. It said incorrect. Solution 6 was prepared by according to the table KEQ2, but make sure you use the exact concentration, okay, for your M1V1. Okay, after use the exact concentration of the stock solution I've recorded, use the dilution formula M1V1. So, I can't use these. I have to use M1V1. So give me just a moment. Let me try this again. So I can't use these. I have to use exact solutions, concentration, so M1V1. So I'm going to do an M1V1. Let me try this out here. I'm going to just do it here. And then if not, because I'm trying to get this part done. I think this is kind of where we got stuck yesterday. They want me to do an M1V1 of these. I think that's what they're saying, right? You do the M1V1 of these because these are the exact ones. Okay. Oh, again. Okay, guys, let me go back to the M1V1 section, the table. Was that here? No, that was the previous sheet. Okay, so this is where I did my M1V1, remember earlier? Okay, so I have to do M1V1 of both. I'm just going to copy everything here. Copy all of this again. And then paste this down here. Okay, so this time our M1 is 1.98 exponent negative 3, right? This is for iron. Wait, am I in the wrong section? Okay, let me get to this part here. Okay, so for this one here, the one where I made mistakes, this one here. But then how do I get the K equilibrium correct? These people, man. Okay. So I cannot use this number here, right? I have to dilute it. When I dilute it, I put this here like that. And so for this one, then, I guess let me try to fix the mistakes I made. Okay, so I'm only writing over the sections where I missed, right? So I'm gonna start. This is, mind you, I have shortened the video by just kind of getting to the point. So this is the part where I messed up for 6. Oh, where are we? Oh, right here. Okay, test solution 6. Okay. So for this one here, I should have 1, 2, 3, 4. This should be 7. 7.92 exponent 1, 2, 3, 4, -4. Is that the case? No, 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 no. Okay. Okay, 7.92 exponent 4. So I need to go over here and see. Man, this is a lot of stuff to keep up with. But remember, so let me try here. 7.92 exponent -4. Let me try that and see how that plays out. So then I have 7.92. Then that changes this one here to 7. But they said there's nothing wrong with that one. These people. Okay. Then this one here would have to be the diluted version, which is, I know it's a lot to keep up with. The concentration here was, they gave me what, 6.98 times, but I have to do, this is the M1. This should be correct then, right? 6.94. Oh, on this one here, the total volume is not 25. Oh my goodness. Okay, you know what? Let me recalibrate. The initial volume for this one here is 5, 5, 5, 5, 5, 5. That explains why things are kind of weird here. Okay. The first one is the one that had 10, 10, 10. This one here is 5, 5, 5. Okay, my bad. That's me. I'm trying to shortcut this process. I need to pay attention. This is the first one. Let me color the first one. Let me actually color the first one so I don't confuse the two, right? So I'm trying to do too much here. Trying to get this thing done. Is there any way I can minimize this? Wait, cancel. Okay, let me just highlight this part so I recognize I'm on top, right? Okay, this is the original one. I'm not working on this one here. I'm working on the bottom one, the one without the highlight. Okay, so the initial amount of iron was 5. I see it now. And the final amount was 10. Okay, 10, 10, 10, 10, 10. Okay. So for this one, our diluted volume is going to be 1, 2, 1, 2, 3, 4. For mine, it's going to be 9.9 times 10 power -4. So let me go back to the next page. 9.9, 9.9 exponent -4. Okay, it doesn't change. This one is not affected, does not get influenced by that part. Okay, to change this part here, our initial concentration is the amount I put here, this 6.98, but I have to do M1V1 for that. So 6.98, the second one here. 6.98, this time we're doing 1, 2, 3, 4. The final here is also 10. It is 10, right? 5 plus 4 plus 5 plus 1 plus 4 is 10. These are all 10 across. So it's 10, 10, 10, 10, 10, 10. Okay. So we got 6.98 as the initial times 10 power -4. 1, 2, 3, 1, 2, 3, 4. I do M1V1 to figure out the dilute concentrations. This would be 1, 2, 3, 4, 5. Okay. So moving on, the first one will be 6.9. Okay, let me copy this over. 6.98 times 10. 1, 2, 3, 4, 5 times 10 power negative 5. 1.396 times 10 power negative 4. 2.094 times 10 power negative 4. 2.792 times 10 power negative 4. 3.49 times 10 power negative 4. Okay, let's see how this goes, guys. Okay, over here, I got 6.9. I need to add a 0 here, times 10 power negative 5. Okay. Really? But how is that possible? Okay, let me try this, guys. Because I don't really feel confident in what I'm doing. Just because if this is not what they want me to do the M1V1 for, then I have to go to the, the original numbers, the 0.2. But let me try this for right now before I start discounting it. 9.90 exponent negative 4. Because once I get that part done, then the rest of it should be a no-brainer. Submit anyways. My apologies for the nuances in this lab. We had to pick something real quick and I didn't really have time to review other things. Wait, what happened to this one here? Oh, okay, now they like the original amount. Yes, they like that part. They don't like this part. That's fine. I can fix this. They like the original amount here. They don't like the new amount. Yeah, this is what I was having issues with is the initial amounts. So we got the right one. This is the right initial amount. Okay, great. We're in business, guys. So I can copy this over. No, copy this, paste it here, paste. That's going to be true for all. Paste, paste, paste. Okay. So the thiocyanate, let's see. I wrote different numbers. Oh, for this one is different. Okay, yeah, because they're different for each solution, right? The iron amount is the same. This second one here will be 1.396 exponent negative 4, right? This one will be 2.094 exponent negative 4. I'm trying to get all this the initial amounts squared away. And then it will make the process easier. 2.792 exponent negative 4. Persevere through. We have one more and then 3.49 exponent negative 4. I have to use a notebook in all of this, okay? So remember, I have to go through and fill in this part here. I'm just trying to see if I can. Let me just delete that part because we don't have these parts figured out yet, right? This is not figured out. This hasn't been figured out. This hasn't been figured out. So it's not confusing, right? We have to figure all these out from the equation. What was the first one? The first one was this one here. So that one should be good now. Let me take these out here. Okay. This first one is correct. So the product size should be correct all the way through, right? And then this one here now, the new number here. Oh, am I fixing this here? Oh, I need to go ahead and retry, okay? Attempt. Okay, confirm. Okay, guys. We will figure this out. When I say we, I mean we. I feel like I'm close. I'm closer now than I ever was before. Okay. So this is iron. We know this is starting point. So this then has to be 9.67 exponent -4, right? And that's the iron part. And this one here will be 4.64 exponent -5. Okay. Okay, for my next one here, and then my K equilibrium should be 522. That's what it looks like. K2. Okay. It's like 522, right? Okay. Let's continue. Next one. This one here, our starting amount, this should be 9.9 exponent -4. This amount is not changing, right? 9.9 exponent -4. Let me see if I can copy and paste this everywhere. That's the same amount. 9.9 exponent -4. -9.9 exponent -4. Okay. So let me start from the beginning. So we got 6 done, right? So 6 should be done. This is done. Now we're moving on to 7. This is 7. Let's start from the left. Okay. So with 7, I need to know what the amount of iron thiocyanate is. Let me go back to my left. It's been a minute. Oh, the amount here will be 5.02. Okay, I have it here. 5.02, 5.0297 exponent -5. Since I have this here, I'm going to copy here, paste this. We're going to add this, minus, paste, minus, paste. And so it looks like we have minus x. So what we have here is 9.4 exponent -4. 9.4 exponent -4. And then go to the right here. We got 1.4 exponent -4. We got -x. And this should be 8.93 exponent -5. And then finally on the product side, we should have a 0 here. 0 plus x, 5.03 exponent -5. Okay. Okay. Let's see what we have for this one here. So K equilibrium should be the same, right? The same. Let me see if I can put this here. Paste. Okay. Yeah, it did it. This on top. And then, okay. So 599? Okay. Man, it's coming together. Okay, second one. Sorry. I play too much sometimes. Especially when something I'm doing is like not the greatest. I'm trying to just make the most of the situation. So minus x, right? And then here we have 9.04. This is my third one, right? And make sure I'm copying the right thing. Now this is my second one. I'm copying this over again. Oh, this is my second one. I've only done one. No, I've done two. Okay, so I'm doing this one here now. Okay, I see where I am. I see where I am. I got a little lost. This is the first. This is the second. Oh, yeah, a lot of spreadsheets. Okay, now I'm working on the third. The third, I haven't inputted it. So 8.052 exponent -5. Yeah, it's a lot to keep up with, y'all. So let me copy this. So I have to think about it. I'm starting from scratch with each set. So minus x, and our x is this value here. Minus x, and our x is this value here. Okay. Okay, now we're good. So over here, this I'm working on 8. 8 is a third, right? So we have minus x. So over here, we should have 9.10 exponent -4. Then on this one here, we have 2.09 exponent -4. This is also minus x. And our product here should be 1.29 exponent -4. And on the product side, we have, it should be 0, negative, oh, no, this is the product, so plus x. And then we have 8.052 exponent -5. Okay. I really hope this works, y'all. Okay. Oh, okay. I haven't done the k equilibrium part, so let me go ahead and copy that over. K equilibrium, copy. Paste. Did it do it again? Yeah, man, this thing is dope. It's great. Sorry. Like, I have forgotten I'm recording this for a class. I'm just like 687. I've forgotten I'm recording this for a class. I'm just like caught up in the moment right here. Okay. So we got a couple more and then we're done, right? Okay. So our next one is absorbance number 9. So solution number 9. So let me start with the solution. Here we had 1.128 exponents. So e power -4, right? Guys, I wrote this down so that it makes it easier for me, just in case you're wondering how I'm doing this fast. I have these all written down. Well, I have the numbers written down. I'm trying to go with the same pattern so I'm not overthinking the process. Okay. I'm trying to stick with the pattern here. So once I have my numbers here, then I go over here, right? I have my initial, my changes minus x, my final will be 8.77 e. I really hope this works. -4. 2.79 e power -4. This is still minus x because it's a reactant. 1.66 e power -4. Like, you have to be focused. It's going to be 0, and then it's going to be plus x this time, and our x is 1.13 e power -4. Okay, guys, this is the last one. Oh, I have to do this one again. K equilibrium. Man, I'm trying to put in the same position relative so it gets the numbers right. 774, y'all. 7. Oh, no. 774. Don't get lost numbers now. Okay, for our last one here, what is this last one here? 1.433 exponent -4. Please work. Please work. It says the same number here. Here is minus that number. And then here is minus x. Okay. Okay. So starting with this one here, I already have these in place. It's going to be 8.47 exponent -4. 3.49 exponent -4. 4. This is minus x. 2.06 exponent -4. This is going to be 0 plus x. 1.43 exponent -4. Then we have to figure out what the k equilibrium is here. $8.21. Find the average equilibrium. So our average, we got 821, 774. Doesn't seem very constant, right? 687, 599, 522. So we got 821 plus 774 plus 657 plus 599 plus 522 divided by 5 is 674. So we'll call it 675. Six, 7, 5. Standard deviation. How do I figure standard deviation? Oh, standard deviation. Man, they are doing us wrong. The standard deviation, our number is 82 for each one? Favors greater than 1. If it's less than 1, favors reactants. Okay. I see. So all I have to do is standard deviation. Man. Okay. Let me see. Let me find a quick standard deviation. Standard deviation formula. Okay, hold on. Standard. Oh, you can do it in Excel? Wait a minute. Standard deviation in Excel, because that will make, to calculate standard deviation in Excel, use standard deviation for, like how though? Oh, I don't want to see a whole video. This is using connection computing at the National College of Ireland. A series of short how-to videos. In this video, we want. Okay, so let's go ahead and figure out the standard deviation since that's what we have left. Oh, and the relative standard deviation. Okay, let's see. Standard deviation should be right here. So I'm trying to figure out how to do it. For standard deviation, to figure out the number of counts, if you're trying to use the formula, you will go over here. I think it's under formulas. There. Oh, sorry. For count, you will press equal. I think the guy I was watching in the video said count, right? Open parentheses. And then you highlight these values right here, and it will say you essentially have 5 items, right? 5 measurements, 5 readings. And then for the mean, I think you can do the same thing, equal. Do we do mean or average? I think AVE, average, right? This one here, open parentheses, Select all 5 data. That gives you the average, right? Standard deviation, you can use the formula, or once again, equal STD, standard deviation. We can use the second one. That's the common one. We have, once again, 5 samples. So press equal for that, and we have what? 122.7. So 1, 2, 3. 1, 2, 3. We can use that. And then relative standard deviation. I don't know how to figure that one out. Let's see if we have it here. Relative standard deviation. I mean, the worst we can do is find out we don't have it here, right? So standard deviation tells you how close or how far your individual numbers are from the average. Our average is 680. The numbers are kind of all over the place, right? So the bigger the standard deviation, the more your numbers are deviating from the average. Let's look at relative standard deviation. So let me press equal, relative. Okay, let me show you where I got these from. If you go up here to calculations, oh yeah, these are calculations. So you go to formulas, right? And the formulas, you have auto sum, you have financial. No way, Y'all, for real, I had to watch a video for this. Okay, I'm looking for standard deviations. We found the average already. We got that one. There's gamma. Oh my goodness. I need to learn all these things. Standard deviation. Okay, we did standard deviation. What about relative standard deviation? I don't know how to do the relative one. Not from here. Yeah, I did that one here. Okay, give me a moment. Okay, so I'm back. We're told to calculate relative standard deviation in Excel. You combine the standard deviation and average functions in the formula like equal to standard deviation divided by average range. Oh, so it's going to be standard deviation. This one right here. So let me open a parentheses. Open parentheses. Or can I just use RSD? Let me see if there's an RSD. Oh, guys, hold on a second. Hold on a second. Give me this. Okay, let me see if I can do the RSD function. My family is about to arrive. My brothers are about to arrive, and they call me. So let me see if I can use equal RSD. Is that a thing? There's no R. This is RSQ. So that isn't a thing, right? So I have to take my standard deviation according to this. I have my standard deviation, right? Divided by average, which is the mean. And then take this times 100. So times 100. Okay. Yeah. So it looks like this is the value. Okay, let's see how we do, right? We got that. We got this as 18. 18.0. Okay, let's see if this works out because this is all I got, guys. Submit anyway. Okay, let me see how I did. Okay, it doesn't really give me a score. But at least, okay, we see some green here. The last time I left, we were up there. Let's see how we're doing. They checked all these correct. Okay, this is progress. We got the K equilibrium correct. They checked these correct, guys. Oh my goodness. And my guests are here. My people are here. My family. And they checked these correct. I am so happy, guys. I know. It's just the nuances of the directions. And then if they check those correct, the rest of them should be correct too, right? Oh no. This should be correct. I probably didn't copy the right thing, but you guys see that for the most part, I don't know if I M1V1 that incorrectly, but it should be correct. So the initial amount here is wrong. Let me see the rest of it. And how did that throw my numbers off? A lot. This number here looks right. Okay. All these numbers look right. Oh, great. So only that one point is off. Guys, this is pretty much it. Only that one number is off, but everything else should be correct. So please, I do apologize for the length of this lab, but hopefully I shortened it well enough for you guys to understand what I did. Once again, I used Excel to really help me with the lab, the math, right? So I wasn't kind of typing in over and over again and getting mental fatigue. Let me go ahead and end this video, and then I'm going to go ahead and share it whenever I'm done. So let me stop.